All right, time to give you some filler extras that didn't happen during class time about the properties of alcohols, and this will be a launching to understand the differences or similarities they might have with phenols and ethers. If you've taken a look at the structures, hopefully it's obvious to you that the alcohols are going to have higher boiling points because of hydrogen bonding. Higher boiling points than alkanes of similar molecular weights. This was in our guided inquiry book that we looked at a little bit together. And the pattern is this: the more hydrogen bonds you find in the compound or more opportunities for it, the higher the boiling point. One example that demonstrates that is shown here. 1-butanol has a boiling point of 117 Celsius, and if you compare that with the neighboring compound here, let's see, advance the slide, the butanol, butanediol is its cousin, if you will. If you look at the differences in the boiling point, there's a dramatic increase in the boiling point by having 2 hydrogen bonding opportunities. So the more hydrogen bonding opportunities, the more the boiling point is going to be raised. So the more hydrogen bonding, the higher the boiling point. You can't always predict how much, but we can guess which ones are going to be higher than others. So the gist is we're going to hear about hydrogen bonding a lot, and so we might as well start now. And it's partial minus and partial plus on the polar bonds of water, shown here on the left, of these water molecules attracting one another. So the partial plus of one hydrogen is attracted to the partial minus of the next oxygen, and it creates a great network of hydrogen bonding within water molecules. So that's what we see on the left. On the right, you have some carbon included. So carbon with an OH on it, well, that would be an alcohol, right? And so hydrogen bonding between alcohol molecules is exactly the same idea, because it's the oxygen that gets partial minus and the hydrogen gets partial plus. And the partial plus of the OH from one molecule is going to be attracted to the partial minus of the next in a network of attractions. So these hydrogen bonding attractions are highly influential in the properties of these compounds. You're going to get used to seeing a lot of little partial plus, partial minus symbols, because we're going to do them often to remind us where the attractions occur. Oxygen always gets partial minus, hydrogen always gets partial plus. So that's the hydrogen, and this is the oxygen. Gray is hydrogen, and red is oxygen. It looks gray in this diagram anyway, so do not overlook the significance of that. The consequence of this is the molecules have high attractions. Hydrogen bonding is strong among intermolecular forces, and the common alcohols are attracted to each other enough that they are not going to be gases. They're going to be liquids up until a certain number of carbons, and beyond that, then they end up to be solid. So you can draw a partial plus, partial minus, as is shown in the circle on the left side for propanol, and that's another way of representing what's shown at the right with the electron density map. As you may recall, the pinkish reddish side is the partial minus, the partially negative side, and the blue side is the partial positive, which corresponds to the polar bond of the OH. It's a very polar bond, and we note the positive and negative poles of that bond with this representation. So be careful that you always notice that the oxygen gets the partial minus, its attached hydrogen gets the partial plus. Do not put them on carbon. It's not appropriate. We didn't even have this discussion in compounds there were only hydrocarbons, because there were no polar bonds in them. They're completely nonpolar. So what's the consequence then? The lower molecular weight alcohols, those with 8 or fewer carbons, or less than 8 actually, are going to be miscible. That means they're soluble, mix well with water. Think about that being mixable is another way of using that idea. And so as long as you don't have too many carbons, in other words, you can mix them with water. The problem is that if you put more and more carbons on there, they're going to behave more like an alkane. So looking at these two compounds on this screen, one would be described more hydrophobic, in other words, not liking water. And the other one is hydrophilic, because it likes water. And so the one that is hydrophobic is more like an alkane. So of these two examples, the hydrophobic compound is the one with a lot of carbons on it. The one with a smaller carbon chain then is going to be more hydrophilic. It much more prefers water than the other. These two compounds, of course, have names. If it's one carbon, this is methanol. And the one on the right, 1, 2, 3, 4, 5, 6, 7, it's heptanol. Okay, so it's going to be able to be miscible with water, and this is 1 heptanol. Miscible, but that doesn't mean it's greatly so. It's going to have much less water solubility than the corresponding smaller compounds. So if you compare the water solubilities of various alcohols, the size of the carbon chain makes all the difference in the world. Larger carbon chain versus smaller carbon chain is going to make a big difference in water solubility. This is a quick generalization, and it works quite well. So be careful as you think through it. I hope you find this helpful. Please ask more questions, and good luck on your homework. See you in class.